it won't take very long really. iPerf is one way to measure bandwidth and a number of other things between two nodes, so you can get an idea what that is. And I'll use that, and you can see here there's even iPerf 3. It's kind of being, there are some new things coming out. I encourage you to have a look at it if you haven't tried, and maybe test some things yourself. So what I have is what I'll do is I'm going to log into my computer at my office. Which happens to be on. It's always on. It runs a bunch of servers for me, various kinds. So what we've got is a laptop sitting here, a laptop which is IITK. Somewhere through the internet we've got Unimelb, and I've logged into that. I can ping it, and so this is still on this laptop. So between this laptop and that node, we can ping it to get some basic information about the round trip time, and we sort of see that the ping is sending a packet, the packet's coming back, so we're getting the time it takes for that to do, and it looks pretty good actually in the sense that if I stop it now, it sort of says at the bottom. Can you see that? Sorry. Can you read that? I guess you can read. It sort of says, okay, we transmitted 18 packets. There was no packet loss on this very short time period. Total time there. And then the round trip time, minimum time, the average time, the maximum, and the deviation. So the average ping time between these two nodes was 430 milliseconds, which is about what you might get, internationally ping time between two nodes. Now I want to ping a third node. I want to try this triangle inequality and see. I have to pick a third node. What I'm going to do is pick google.com. I'm going to pick one of their servers and we'll ping that. Let's have a look. There's a whole heap of different addresses. Google.com is telling me this IP address. So I'll ping that from my computer in Melbourne. We're getting a similar sort of readout, much less ping time. Google has lots of servers, right? Now, again, there was no packet loss, about 30 milliseconds. So Google, go over here somewhere, I'll just put Google, and about 30 milliseconds. That's much closer than what this laptop is to my office computer. Why did I actually want the IP address? Why didn't I just say ping google.com? And the reason I did that is because if I were to get the google.com from, say, here, you could see this IP address is different what it gives me for when I look for google.com from Camper. It's giving me a different node that's somewhat closer. So I can't just use google.com. I've got to use the actual IP addresses. So I'll ping that same IP address up here that we pinged, and we'll see what we get to finish the triangle off. Now we get about 252 milliseconds. It's very consistent, 252. So I think you can see these numbers don't make a lot of sense. In terms of the triangle inequality, the sum of these two things is actually quite a bit shorter than the time from there to there, right? So it doesn't hold. And that's sort of not surprising because these paths that things take are not really the shortest ping times, what goes through the network. They do try to take the shortest path. Obviously, routers are trying to get the packet to the other place as soon as possible. But Google has got its own network, and it's very high speed and so on, very high performance network. It's giving me, the ping time to google.com here. If I just take the nearest one, is, this is going. It's a little bit varying now, actually, isn't it? But it's quite small, so. What would be really nice if I could kind of borrow Google's network. I could potentially send packets to my computer at Melbourne a lot faster than I could send if I just send directly, if I go through this third party. Some research was done in this space, looking at the triangle inequality on the internet in various ways. It does hold, actually, in about 80% of the cases. At least that was when the research was done. About 80% of the samples that you take, you'll see that the numbers more or less make sense. That of course, these are real numbers. They have a variance and so on. But statistically, about 80% of the time that the triangle inequality will hold. About 20% of the time it won't. This is a clear example of where it's not really holding. And so there was some research to say, we can maybe make things work faster if we find these third party points where we can transmit packets through other nodes in the network to try to get better performance in certain ways. I think it's probably not holding more and more as we get a lot of the very big internet companies that have all their own networks and can provide a kind of oasis, if you like, on the network where everything goes a bit faster than if it just goes through the standard paths. So that's just some basic information. You use ping just to see if something is alive a lot of the time as well. So that's that. Now I can run on my machine in Melbourne the iPerf server. So if I'm going to test bandwidth, I need a server running on one of the machines, and then from this laptop I'll run a client. It will connect and it will start sending some packets and measure the time it takes to send those packets, and then that kind of gives us an indication of the bandwidth. So I'll run the server so now it just starts up. It says it's listening on a port number, port 5001. By default it's going to use TCP. So now I'll connect to it with the I'll just run it just exactly like that. It will connect. It says it's connected. It's taking some time now, sending some data that it's not showing us, I think, for about 10 seconds. And then it comes up with a measurement of how long did it take, was it sending data for, how much data did it transmit in megabytes, and then a calculation of the bandwidth in terms of megabits per second, right, between these two nodes. The server also does a similar calculation, but you can see the numbers are different. You'd think that the calculation would be the same, but things vary a little bit. The time here that the server saw the data coming in was a little bit longer, and that can be because the client is communicating, this laptop's communicating with a router nearby that's buffering information. Potentially the client finishes sending the data in a shorter period of time than what the server finishes receiving the data from the beginning to the end. So there are little nuances like that make the calculation different the way that it's seen. But if we increase the time, I think I can make the time for 20 seconds instead of taking about 10 seconds. I can tell it to take about 20 seconds. What I'll do is, so that we can see, can I stop? Yeah, I just aborted that. I can tell it to print something out every second as well, so that we can sort of see a little bit more what's going on. So every second it's transferring some more data. It has a kind of different calculation of the bandwidth that's going on between these two, and this only the client's printing that out. So if we go for a longer period of time, we kind of get a bit more reliable estimate of what the bandwidth will be. I mean, I could run this an hour from now and maybe get a completely different reading, because maybe there's something else that's happening in the network, the way that it's working. So so we got down to 20 seconds, and then the total being, so over the 20-second period, we transmitted 10.9 megabytes and 4.5 megabits per second, and it's kind of very close to what was observed at the server as well. So these are TCP. This is one TCP socket that's just trying to write the data as quickly as possible and then see how much data we write. One TCP connection between the client and the server. What if I had more TCP connections in parallel between the client and the server? So if I had 2 or 4 or 10 of them all running in parallel, would I get better bandwidth, better throughput, be able to transmit more, or would it be about the same, do you think? So I open up many more connections at the same time. We can actually try that. So here we had about 4.54 megabits per second. I can tell it to open up, I'll do 20, I can tell it to open up 20 concurrent connections, all 20 different connections, all of them trying to push data to the receiver. And there they all are. There's a bunch of different connections. Now it's printing out this report once every second, but it's printing them out for all of those different 20 connections that go through, how much data is being transmitted. So we wait for the 20 seconds and see what the aggregate, the total bandwidth or throughput that we achieved. Did I say 20? Yeah, 20 seconds. So actually it went for 23.2. And we've got 12.2 megabits per second. Now before we had about 4 megabits per second. So we've kind of, by having multiple connections, we've somewhat increased the throughput. Now why is that? I mean, isn't a single TCP connection trying to make as much use of the bandwidth as possible? Right, I mean, right, so some of the parameters of TCP where it's got a window size. There are buffers, right? So when we have more of them, then we kind of have more space, we have more buffers, we can have more outstanding packets at one time, more acknowledgements coming through the network and so on. So we've essentially got more resources. So one of the observations that the file sharing community made was, and this is where you get, anybody heard of BitTorrent? Probably some of you using BitTorrent, right, to share files or whatever. I actually met the inventor of BitTorrent, Bram Cohen, a number of times at some distributed systems conferences. Anyway, so one of the observations is that if you get a lot of little pieces of data from many nodes, it can be faster than getting a big piece of data from one node, right? Because you've got many more opportunities for transmitting the data. And so that's what happens in a file sharing system, is that you'll often have many connections coming to your computer, downloading from a lot of different sources to get the one file, rather than just from one source, right? So it's kind of interesting. You can use this to explore a little bit more the window size and so on, and other parameters of TCP. You can also do UDP, and so I have to stop the server on my computer and start it up with -u, and now it says it's listening for UDP, and I can tell this to transmit as UDP. Now what this will do is it will transmit the UDP packets at a rate of 1 megabit per second, and then it will observe effectively how many were dropped, how many were lost, was there any what is the jitter, and in this case we didn't lose anything, right? So we transmitted 1,785 packets. There was no loss. There was a little. This is the jitter. There's a little bit of jitter. So if you transmit a packet every second, it doesn't at the server come every second. It comes you know, they get spaced out a little bit, right? A little bit like cars driving down the road, especially here in India. I mean, it's very regular in some places, but here I found I'm not sure I could drive here in India. Everything gets spaced out, and there's all different things, right? It might start off regularly, but the packets, when they get to the other side, this is called jitter. And so there's a bit of jitter there. We did achieve the 4 megabits per second. Of course, we knew that we could, because from our previous measurements, we could get at least 4 megabits per second with a single TCP socket. And this is the number of bytes that we transferred. But let's try to really push it. Let's say I'm going to assume that I've got 100 megabits per second bandwidth between these two nodes. So I'm really going to send a lot of packets from one node to the next, to the other, sorry. So we do for 20 seconds, and you can sort of see the rate, the bandwidth that it is indeed that it's transmitting at. So actually, there was one packet lost. See, one datagram received out of order, and we achieved a 26.1 megabit per second rate of sending these packets. That's pretty good, actually. I could open up I was going to open up another window to a computer at my home, and show between home and work. But I think that you see, how this tool can be used, and how you can try to investigate the properties of between two nodes in the network. You might use these values then to when you're trying to optimize location of data in the network for doing your regeneration, and I think we show later, this becomes a kind of cost. So what is the cost of sending a block from one node to the other? Is it, how do you rate that? And this is how you can kind of find out what that is. Are there any questions about these tools or what I'm doing here?